Hi, welcome to my talk, MicroCeph Simplifying Storage for Laptop and Data Centers. My name is Peter Sabaini. I work for Canonical, although this is not a company-sponsored talk. I've been working with storage system for many years, mostly with Ceph, but others also. And yeah, I'm going to give you a short overview of our storage landscape, Ceph, and then finally MicroCeph. So circa 2000, the storage landscape would look roughly like this. You would have either expensive proprietary gear like EMC or NetApp filers. And I'm not going to go into much detail here. This is a Linux conference. I don't need to tell you why proprietary gear is problematic and can bite you. Or you would have some old, well-tested, tried-and-true open source programs like NFS, IceCasi, Samba, VRBD, which are all fine, but they have their issues. First one is none of these traditional tools are high available out of the box. Yeah? So if your NFS server goes away, your clients will hang. And so this can be problematic, even if you have redundant storage, because you might need to take it down for maintenance or something. So you can make these systems highly available, but you need extra components for this, like pacemaker, and these things, they can be brittle and difficult to set up. And also they typically will require you to have a second standby system, which basically does nothing most of the time except wait for a failover. Second thing is scalability. So if you have an NFS server, you can put more disks in it, you can put more network interfaces in it, but there's a limit to how much that will scale up. And distributing the load of such a system across many servers is difficult. Finally, flexibility. You typically have to handle a file system and block devices separately. And at the time, so before Ceph was invented, there was no open storage system, to my knowledge, that would expose object storage like Amazon S3 does, which is super popular these days. So that was the landscape when Ceph came into play. I'm just going to give you like a 10-kilometer overview because I could talk longer on Ceph. What is Ceph? Ceph is software-defined storage built on the premise that you have intelligent daemons that are managing your object, your data, and striping it across many objects. And it's a unified system, so that means you can expose your storage either as a block device, or you can have object storage or file systems exposed, all with the same, backed by the same backend. One of the core ideas of Ceph is that you don't have a central gateway. Clients for I/O, clients talk directly to storage nodes. You have two essential components. One is the monitor component, which is highly available. It's running a consensus algorithm, which just keeps the cluster topology, so it knows which disks are where and where the data is, etc. But apart from this metadata, the monitors never come into play. If clients need to do I/O, they're talking to storage nodes directly. Ceph is built on the idea that you will keep your data redundant for safety. There's many different ways you can set this up, but a default and a very popular method is to just keep 3 plain copies of your data, replication factor 3. That is what we'll get out of the box. Ceph is self-healing on node failure or on any hardware failure, really. So if a node goes away or a disk goes away, it will rebalance your data automatically. It makes a focus of consistency first. So it's CP in the CAP theorem instead of availability. What this means in practical terms is it will refuse to accept I/O if it cannot guarantee its consistency. Yeah, and this architecture with the different storage nodes makes it very easy to scale out. There are systems in place with hundreds of nodes and thousands of disks. One thing you can do with Ceph is you can determine your failure domain. The failure domain is basically the smallest unit you want to be able to afford to lose with your system still being functional. So this begins at the levels of a disk. You can lose one disk, and your system will be functional if you have like 3 times replication and 3 disks. But you can scale that up to a host, which is the default with Ceph. So it will take care to place your data on different hosts so that you can lose one host and still have a running system. Or you can go up from that. So with a larger cluster I used to operate, there were different rooms which were insulated with firewalls, so not the network firewalls kind, but the physical with the burning gas firewalls, so that one room could burn down and the other rooms would still serve your data. What does this look like in practice? So let's assume we have this simplified schematic of a cluster. One node dies or needs to be taken down for maintenance or whatever. So the cluster is running a kind of heart-beating scheme that goes from the storage peers and also from the monitors. And after a few seconds, typically, they will notice that the node is not responsive anymore and will mark this storage node as down. So at this point, you only can guarantee a replication factor of 2. The monitor will update the clients and say, okay, this storage node is not responsive anymore. And after a grace period, to prevent flapping, data from the store 1 is copied elsewhere to get back to replication factor 3. So, and if sometime later storage 1 comes back to life, it will notice, okay, we have this data elsewhere as well, it will prune its extra replicas. So, this is a quick overview of a Ceph. What is MicroCeph? MicroCeph is a cluster in a package. The problem statement is deploying and operating a Ceph cluster is a complex thing. You have many distributed components and configuration you need to keep in sync. You have a complex bootstrapping procedure, and the hardware requirements are not trivial, so you can't just install it on the laptop and be done. So it's a single package Ceph cluster. It comes in one snap package, and so this is my kind of hello world example. You need only 4 commands to get up a functional cluster. And you can do this on your laptop, don't even need an extra block device. So my hello world example, sudo snap install MicroCeph, bootstrap it, and for this example, for the simplest example, add some simulated block device loop files. Three pieces, and yeah, that gives you a functional cluster. So this is the standard Ceph status command. See, we have a healthy cluster. One of the OSDs has not finished booting up yet, so you have 2 up in the cluster, but there's 3 known in total. The snap package format, we use the snap package format for isolation because all of the userland software from Ceph runs in a single snap, in a single file, and it just needs the kernel from the host system, network, and block devices. This makes it easy to keep it consistent across operating system, and also gives the level of safety and security because the snap software cannot just access any interface or any device on the host. Architectural, quick overview. You have the MicroCeph daemon, which is a service daemon that manages the other services and also keeps a configuration database, a distributed configuration database, and exposes an API. And inside the snap, we also ship a MicroCeph CLI, so the command line interface. But that CLI is just another API client. All the things you can do with MicroCeph are exposed via an API, which is very useful for integration with custom clients. So I've already shown MicroCeph can scale down very well. You can go down to a single node, single disk systems. But it also can scale up to some level. I'll go into that later on. What it also does is it manages your application, your failure domain. That means if you install a single node system, like we did just before, it will configure OSD level failure domain. And as you scale up, if you go over more than three nodes, it will switch to a host failure domain automatically. So that means single node clusters work out of the box, and as you scale up, you get the added safety automatically. You can go up for larger failure domains as well, but MicroCeph doesn't really know how the topology of your data center looks like, so it won't try to manage, configure failure domains like racks or rooms automatically, but it also will not step on your toes if you want to do this yourself. In terms of scalability, MicroCeph shares some scalability traits with Ceph, so it scales very well. It is, however, bound by the Raft algorithm of the distributed database. I personally tried it with 80 plus nodes, like 84 nodes, and that worked well. I would not go very much farther than that, though. How does it look with clustering MicroCeph? Basically, you install a single node system, run a bootstrap there, and then you need to get the token for other machines. So like SSH into the bootstrap node, tell the bootstrap node you want to add another node, and it will return a token. And you can then pass in this token to the next node that wants to join the cluster. And then you would need to add some disks, etc., of course. So you have your beautiful cluster. How do you make use of it? One very popular and widespread use is exposing storage as block devices. This is the job of the Rados block device facility. Basically, you have a block device with data that resides in Ceph. This works out of the box. No extra services are necessary. Your management comes with the Ceph tools like the Ceph and RBD programs. Linux supports this as well. So there's different ways to actually consume these block devices, and Linux supports a kernel module that can make use of this and basically map the block device onto a local machine. Or you can use it with QEMU, KVM, that also has built-in support for this, but not in the kernel module, but in user space. Still, you will need a setup for this with Ceph client tools. These come in a package. Typically on Debian Ubuntu, it's the Ceph common package, and there are similar packages for other distributions. Second thing is CephFS. That's very similar to RBD in terms of support. Not going to go into too much detail here. Basically, it supports a file system you can use and mount on clients with the data residing in the Ceph backend. And finally, a very popular use for cloud-type systems is the object storage. You need an extra service for that that's called Rados Gateway, and that provides an S3-compatible object storage for Ceph. MicroCeph Snaps ships with these services included. You can enable it on a node by saying MicroCeph enable RGW. And it also comes with the Rados Gateway administrative tools that are standard with Ceph. Yeah, and you would access this with standard S3 clients like the S3 command line client or the Boto library or similar. There's a range of clients you can use for that. Right, so I've been talking what we all can do. Let's show how that works. I've pre-recorded this demo because I'm very bad at talking and typing at the same time, and also it can speed it up a little bit. So first I'm going to install some snaps. I've prepared 3 VMs for this demo. So first thing is that we need to install those snaps. And as I mentioned before, we're going to bootstrap on one node. We could pick any node, but I'm going to pick node 0, just out of habit. And yeah, and all those VMs come with one virtualized block device included, which we make use of later. Yeah, excuse the typos, please. Yeah, so we're getting a token from the Bootstrap node. And SSHing into the joiners, and tell them, or tell MicroCeph there that they need to join that cluster. So yeah, let's quick look. Indeed, we have 3 nodes here with the default services, but no disks. So let's add some disks. I'm again looping through all the nodes, and the block device I've added for the virtual machines is called devSDB, so I'm going to add that. Need to wait a bit until everything comes up, but then we can check status again. More typos. Right, so here we are. We have 3 OSDs, we have 3 monitors, a manager service, etc. So next step, we are going to enable Rados Gateway. That's easily done. And we can see in the service overview we have 1 Rados Gateway service now. Rados Gateway has extra user systems. Just going to pause it here a little bit. So we need to create those users. That's unfortunately very ugly output. I'm sorry about that. Users that I then add in the configuration for the S3 command line client here. So this is the configuration for the S3 command line that I had prepared. And now I can use that to create a bucket. Check that the bucket is accessible, although empty. Yeah, and gonna to upload some data in there. And okay, right, we could put a picture in there. And now we see, okay, we're actually using some data now. Next step is to enable RBD. The Rados Gateway facility did this automatically, so generally Ceph manages the storage in pools, and you need to create a separate pool for every application. So Rados Gateway created its pools itself already, so that we needn't to do anything here. For the Rados block device, we need to create that pool explicitly. And we are going to create the RBD pool, which is the default name the RBD tools expect. So I have prepared a 4th VM here, node 3, which also has some configuration. We need the cephconf, and minimal cephconf is to tell it just where to access a monitor host. You could put more monitor IP addresses in here for failover, but I was lazy and just put in that one address. And you need some credentials. And because I'm lazy, I mentioned that again, I just copied the admin keyring over. Just stop a little bit here. Yeah, and to have the Ceph tool and the RBD tool here available, I installed also the Ceph command package. I had it installed already just to show it's there. Okay, so I looked if there's anything in my pool. There's nothing in my pool because I just created it. So let's put something in. In creating a test volume of 4 GB size. Well, here it is now. We can get some more information about this test volume. And then the RBD map basically tells the kernel to expose this volume as a device locally. So by default, they're called RBD and then some number. And that's just a regular block device. So can create some file system on it and mount it. Yeah, and here we go. A small extra data partition. Yeah, so need to be root, of course. Yeah. Yeah, just to show that we can actually do something more interesting than touch a file. Just gonna create a tar here. again with the root. Yeah, and here we go. And let's quickly check how that looks here. So we see we had some client I/O here, and our test volume actually is using some data. So next thing I can do, just to say, okay, that doesn't live forever in that Ceph cluster, we can export that image as well. And it's a file system image. And this could be used, for example, to have a loopback device locally. That's the loop 4 here. Yeah, so I'm just going to show that this is the same data in here. Yeah, here we go. So that was the demo. How are we doing for time? Oh, it's okay. So I've extolled the virtues of Ceph and MicroCeph a lot. I'm going to just quickly summarize what are good use cases and what are less good use cases. MicroCeph is very good at simplified deployments, I think. Scalability, I already mentioned it, up to 80 nodes. I've tried personally. I think it would go a little higher than that. I have not actually tested to breaking point. MicroCeph and Ceph in general is very good at highly parallel large block size I/O. So you can get fantastic throughput with this if you have the correct workloads for this. And it's also very good at reliability, so the consistency that really works. So I've never lost data in all my years of Ceph. I've had plenty of problems, but never lost data. Bad fits, what doesn't work that well. So if you need very large scale deployments, several hundred nodes, I would go with plain Ceph, not MicroCeph, just because of the added flexibility. And a cluster of that size, you will need some people that know this very well anyway. So yeah, you could just go with plain Ceph. Ceph in general and MicroCeph, the extension, is not very good at low latency. Yeah, so it's generally, this is because of the consistency and replicas. So what happens if you write to a storage node is that the storage node then creates 2 replicas, and then in case of synchronous workloads, it will only report back until it knows that 2 copies of the data have been written. So I've had this with several customers as well. Yeah, so they put in expensive hardware, fast NICs, NVMe, etc. And then said, okay, I'm only getting a couple thousand IOPS in these workloads with small block sizes. And that is just because of that. So this is, by the way, a typical database workload, right? Synchronous I/O with small block sizes. It works, and we have people that are running MySQL, etc., on volumes from Ceph, but it will not be fast. Ceph for the management, and especially in failover situations, does need some resources, memory mostly. So for very small nodes, it's not a good fit either. And the other thing is, it kind of expects low latency links. I would not install a cluster across a wide area network. So just very quickly for the integrations, block device storage is very common in OpenStack installations with Ceph. You can use MicroCeph as pretty much the same way like you would use a regular Ceph cluster, using the Ceph driver for RBD. Similarly with Radius Gateway, it can connect to Keystone and Nova for object storage. And one of our newer products, Canonical OpenStack, which is OpenStack built on Kubernetes, which works pretty well, I have to say, uses MicroCeph by default. Similarly with Kubernetes, behaves the same way like regular Ceph. You have the common storage interface. There's a project called Rook that uses, that integrates Ceph with Kubernetes, and you can use that for convenience here. Finally, MicroCloud is a lightweight cloud system that also uses MicroCeph by default. And yeah, a fun but interesting, very useful use case is the GitHub action we have. so that you have a GitHub action that can provide S3 interface for your testing or CI uses. Okay, that was what I had to tell you. Any questions or thoughts? And we have a microphone somewhere for the benefit of the stream. Thank you.
Is MicroCeph only available via Snap, or do you also provide Docker distributions?
It's only built in Snap. Snap and Docker are pretty dissimilar in the interfaces they offer. Snaps come by default with Ubuntu, but you can use snaps on other distributions as well. So I know that there's documentation for CentOS, for RHEL, for SUSE, for Arch Linux. And I think I've seen Gen 2 mentioned somewhere, but I'm not that one I'm not sure about.
I just have a general question.
Mm-hmm.
Just a general question. Because I know that Ceph a few years ago had a big problem with NVMe drives because it wasn't made to use NVMe storage in the background. It was thought to just use spinning Rust in the best case. I know that like 3 or 4 months ago, the new Crimson Reef version of Ceph got released. Would you have any experience like how the performance improved for random I/O?
We get 1.5 gigabyte per second to 3 gigabyte per second writing on this devices.
So NVMe in general should work fine. I mentioned it before. Sometimes people expect like, hey, I have got 1 million IOPS from this NVMe locally. Why don't I get 1 million IOPS in Ceph? It doesn't work that way. But NVMe in general works fine. Crimson is an ongoing project. It's supported for some use cases in the latest Ceph release, but it doesn't have huge performance improvements, I'm afraid. Mm-hmm. It's lighter on CPU in general. It also depends very much on the backend, because you can use Crimson with a traditional BlueStore backend. Mm-hmm. But there's also a new backend that goes with Crimson that's called CStore, which promises to be faster, but still is not production ready yet.
Okay, it's still in the beta or the alpha, likely. Mm-hmm. Thank you.
Sure thing. Yeah, and on the topic of performance with NVMe, this is also a case of throughput versus latency. Yeah? So throughput works fine if you can parallelize your I/O, and you get great throughput, especially with NVMe. But the latency for small block sizes or something, that is not the same as like local storage. Yeah. So in practical terms, getting much lower than 700, 600 microseconds for a single I/O is hard. Okay, thank you.